Hello and welcome to the video for lesson 5, the content video. This will be the first of the videos. It will be a little bit longer than maybe some of the other ones, and so maybe halfway or so if you want to take a break, step away for a few minutes, and then come back. But I wanted to just kind of put all the content in one video rather than separating it like we did a couple lessons ago. Again, this is lesson 5. For Precalculus 1, this is going to be the video on rational expressions, rationalizing, and solving nonlinear inequalities. Let me share my document camera here with you guys. Maybe. Come on, Zoom. Mhm. All right, what is happening here? Slow here today. Sorry about that. Come on, Zoom. Okay. Oh, sorry for that delay. I don't know what that was about. Hopefully, we don't have issues as we go ahead here. I don't know. This is really slow and glitchy. All right. So, as I said, the first thing we're going to talk about is something called rational expressions. And something, so again, as always, if we look at the first part of this word, ratio, that means a fraction. So a rational expression is when the numerator and or the denominator. What is happening here? Why is Zoom asking me this? Don't send, just quit acting up, that's all. All right, so numerator and or denominator are polynomials. So if you want to maybe think of this as like fancy fractions. So instead of something like 1/2, which is also a rational expression, right? So it's a polynomial of 1 and a polynomial 2, and it's the ratio of those. But stuff we're going to be looking at more often with this section is something like 2x over x minus 1. So we have the polynomial 2x, we have the polynomial x minus 1. It doesn't just have to be degree 1. You could have like x over x squared plus 1. That is also a rational expression. So the issue that now pops up for us is that we have these denominators with variables in them. And so we now have to be concerned with something, and this is going to be the first time we talk about it, is something called domain. We're going to talk about it later when we start getting into functions. And for any of you guys that are going to be going on to calculus, you're going to use domain just about every single day. So this is a critical concept that we're going to be learning this semester. And what the domain is and what it means is all possible x values. So what X values can I put in there? What X values am I not allowed to use? And so we're going to have three concerns. We're only going to look at two of them today. The first one, the first concern we have, which obviously with the denominator, we can't have a denominator of 0. So we want to first ask ourselves, is there a denominator? And if there is, to figure out what our domain is, then we set the denominator that it cannot be equal to 0. So we set up this equation, or maybe non-equation, if we want to call it that. Solve for x, and whatever that value or those values of x are, we can't use those, but anything else is fine. The second question that we're going to be asking as we discuss domain here is there an even root? So in that situation, so we don't want negative square roots. We don't want negative fourth roots, sixth roots, etc. The odds are okay because I can do like cube root of -8 and get -2. So that's okay, but when I have an even root, that becomes an issue for me. So to find out what the domain's going to be for those guys, I set the radicand, and that's why I stressed that guy so much when we were talking about radicals. And that's the value under the root symbol. Set that greater than or equal to 0. And then you solve that and it tells you, okay, these are the values that the function can have. Lastly, so those are our only two concerns. If I don't have a denominator, if I don't have an even root, so let's say, for example, I have, well, let's just do x minus 1. So is there a denominator there? No. Is there a square root, fourth root, anything like that? No. So that means what? That means I can have any value of x that I want. It's not going to cause me a problem. It's not going to give me negative square roots or even roots. It's not going to give me a 0 in the denominator. And so for this kind of expression, we say the domain is all real numbers, which in interval notation is going to be -infinity to +infinity. Now, the nice thing about rational expressions is that they follow essentially the same kind of rules and the same kind of process that regular fractions follow. And so if I want to simplify rational expressions, if you remember back to when we were doing fractions, if I have a times c over b times c, I can cancel out both of the c values and just get a over b. Well, that still works with rational expressions, but I have to be careful because, again, if you remember back to when we were just doing fractions, I talked about how if we have pluses and minuses, I have to cancel out everything or nothing. And that's where this really comes up here. So let's say I wanted to simplify x squared minus 1 over x squared plus x minus 2. Well, I can't cancel out the x squared, like, oh, here's an x squared, cancel it. Here's an x squared, cancel it. So all I can do in this position is factor the numerator, which is a difference of squares, x plus 1, x minus 1. Factor the denominator, which is x plus 2, x minus 1. And now this entire x minus 1 cancels out with this x minus 1. And I'm just left with x plus 1 over x plus 2. And again, that's it. So I can't say like, oh, let me cancel out both of these x's and my answer is 1/2. That's not true. You have to cancel everything or nothing. And so that's where you end up. We also have within this rational expression the complex version of these guys, which is something called a compound fraction. And this is just a fraction with more fractions. So for example, I might have something like 1 plus 1 over x divided by, let's say, 3 over x minus 2. So I have a fraction, numerator, denominator, but then in the numerator and denominator, I have more fractions. So we have two ways to solve these. The first is like we did when we just had numbers. Combine the numerator, combine the denominator, keep, change, flip. So that's one way. That can get messy though, because depending what fractions you have, you could get some really messy fractions in the numerator and denominator. And then trying to keep, change, flip, you got all these polynomials all over the place that you're trying to keep track with. So another way we can do this, which cleans up this entire problem, is to first find the LCD, least common denominator, of all the terms. And then multiply every term by that LCD. So if I look at this one here, this is like 1 over 1. This is 2 over 1. So my common denominator then would be what? Just x. I have an x here, I have an x here, 1 and 1. So it's x. Now, the math behind, well, wait, why are we just multiplying every term by the LCD? Well, technically what I'm doing is multiplying this entire expression by the LCD x over x. Because x over x is what? It's just 1, right? Simplifies to 1. So I'm changing how this looks, but I'm not changing the value. And so then if I'm multiplying two fractions, what do? I multiply the top fraction, I multiply the bottom fraction. So I'm multiplying this guy by x. 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 So that's why I say just multiply every term by the LCD. That's the math behind it. Why we're able to do that is because essentially I have that numerator and denominator that's getting multiplied by everything. So when I do that, there's nothing to cancel out here. So I just have x times 1, which is x, plus here, this x cancels with that one. So I just have 1. Here, this x cancels with that one. I have 3. And then nothing cancels here. So it's minus 2 times x, which is 2x. And that's it. That is your answer. That is how you would simplify this compound fraction. So we're not having to combine the numerator, not having to combine the denominator, just and then keep, change, flip. We just multiply by the LCD and we get rid of that compound fraction part. I just get a regular rational expression. And if I can simplify it, great. But if not, that's it. All right, next concept. So a few lessons ago, we did rationalizing. Let's call it rationalize 1.0. And we had something like what? 1 over root 2. And by our shortcut method, we multiplied the top by the radical, got rid of the root symbol in the bottom, root 2 over 2. So those are pretty straightforward, not a lot of calculations involved. But now we're going to rationalize and call it 2.0. And this is where we have a binomial, so two terms with a radical, or it could have two radicals. And so to rationalize this kind of rational expression, what we're going to do is multiply the numerator and denominator by something called the conjugate. So you're like, okay, great, but what the heck's a conjugate? Well, very simply, the conjugate, let's say I have x plus y. The conjugate of x plus y is just x minus y. We leave the values the same, x and y, x and y. The only thing we change is this middle sign. So if it was positive here, it's negative here. If it was negative here, it's positive there. And the reason we do that, and we'll see with the example, is because when we FOIL it, the outside and the inside terms are opposite. They cancel each other out, and then we get rid of the radical. So let's look at an example real quick. Let's say we want to rationalize 1 over 1 plus root 2. So the conjugate then would be what? It'd be 1 minus root 2. And I have to do it in the top and bottom because 1 minus root 2 over 1 minus root 2 is what? It's just 1. So again, essentially, I'm just multiplying this whole thing by 1. So I don't change the value. I just change how it looks. So the top stays 1 minus root 2. The bottom, when I FOIL it, I get 1 times 1 is 1. But the outside is 1 times negative root 2, which is minus root 2. And the inside is positive root 2 times 1, which is positive root 2. And these guys are opposite, so they cancel each other out, which is what we want. And then I just have last, positive root 2 times negative root 2 is minus 2. So root 2 times root 2 is root 4. Square root of 4 is 2. So the root symbol goes away. Simplify this. So I have 1 minus root 2 over 1 minus 2 is negative 1. So bring that negative sign up. So you have negative 1 times 1 minus root 2, which if we make it look nice is negative 1 plus root 2. Oops, the sun's coming in here and hitting that now, huh? Let me move over. So that is rationalizing, we'll call it rationalize 2.0 when we have that binomial. Now, I'm going to move on to nonlinear inequalities. So if you want to like hit pause for a second, take a quick break, or maybe a long break. I don't know. Maybe you're tired of watching math videos. And then come on back. You can watch this, or if you're a trooper, then let's just power on. So again, what we're looking at here is what's called a nonlinear inequality. And so nonlinear, so we've already done linear inequalities. That's when we had x to the first power and we solved it like a linear equation. We just had to be worried about the inequality if we were multiplying or dividing by a negative number. That was kind of the only trick there. This is not so much. This is a lot more tricky. And this is basically when we have a product or a quotient. So we have things multiplied by each other, or we have things divided by each other. So for example, we could have something like x plus 1 times x plus 2 is less than or equal to 0. This is a nonlinear inequality. Or something like x over x plus 1 is greater than 0. And people always make the mistake like, oh, I just multiply both sides by x plus 1 and then solve for x. That's not how you do these. When we have a nonlinear inequality, there are several steps, 9 steps, actually, I'm about to show you here, that we have to follow in order to solve these. So what are the steps? First of all, we must have 0 on one side of the inequality. So these examples I showed you, we had 0 already, so there wouldn't have to worry about that. But if this was like a 1, or this was a 1 or a -1 or 2 or whatever, we have to first add or subtract that to get it over, because I can't have that. I can't have anything but a 0 on one side. If I did have to do something to get a 0, then whatever I move around, I have to combine the non-zero side into one term. Let me close those blinds real quick so that's not shining on the paper. A little better. And turn on this light. Okay. Step 3. If possible, or if necessary, we have to factor the non-zero side. So we got it into right side is 0. We have it as one term. If this was like foiled out already, we'd have to factor it. If there were multiple values here, we'd have to factor it. Because then what we're going to do, I'm going to switch to red here because it's that important. This is the critical here, is we set each factor equal to 0. Let me write it out even. Equal to 0. So not greater than 0, not less than or equal. It doesn't depend what the problem was that we started with. We set each factor equal to 0. This is our critical step because this gives our what's called critical points. And that's where this product or this quotient switches from a positive value to a negative value. Once we have that, we draw a number line with the critical points. So let's say, for example, I found out, okay, my critical points are -3 and +2. So I draw this number line, okay, -3, -2. I'm sorry, +2. -3 and +2. Step 6 is I want to pick test points in each interval. So this is -infinity down here. This is +infinity up here. So something between -infinity and -3, let's say -10. It can be any value. It could be -100, it could be -4, just as long as it's between -infinity and -3. Something between -3 and 2, well, let's go with 0. And something bigger than 2, let's go with +5. crazy blind, still shining here. So we pick those test points in each interval. And step 7 is we plug the test points into the inequality. And I do this to determine if the interval is positive or negative. And so I'm going to do this for every interval. And this is where it kind of gives us an idea if we're doing it right, because if I'm doing it correctly, if done correctly, then each interval will alternate between positive and negative. So let me close this blind again. I don't know what's going on. Okay. So let's say I put in -10. I simplified the inequality and I found, okay, this is a positive number. I don't even care what the number is. I just want to know, is it positive or negative? And then I plug in 0 and I find out, okay, this is a negative number. Don't care what the negative number is, just that it's negative. If I plug in 5, this better be positive because these intervals should go plus minus, plus minus, plus minus, etc. If I had like plus, 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 I know I did something wrong because you can't have the same sign one interval to the next. Like I said, these are what's called critical points. This is where that inequality changes from positive, then to negative, then back to positive, etc., etc. Once I have that done, my 8th step is to choose the interval or possibly intervals. We could have more than one. So interval or intervals that make the inequality true. So let's say I had my product or my quotient is less than 0. Well, less than 0 means what? That's negative. So I want the negative interval, which is right here, which is going from -3 up to +2. And so my last step then is I have to determine if the endpoints make the inequality true. So I can determine whether to use parentheses or brackets. So let's say that I went through this, I plugged -3 back in, and it's like, oh, that makes the inequality true. Therefore, -3 gets included. So I put a bracket. But then I put in 2, and it's like, oh, that doesn't make that true. So I can't use, or maybe if I have a quotient, it makes what? The denominator 0. So I can't have a denominator 0. So therefore, 2 is not allowed. So I put a parenthesis around the 2. So we're going to look at a couple examples of this in the sample problem video. But for now, I just want you to know the steps. And then once we work on these examples, then you'll see how it all plays out. So that's it. That's the end of the lesson 5 content video. We will see you guys in the second video.